SwayamPrabha. Digital India. Educated India.
So students, today you are going to start a new topic, that is a special kind of phase transformation known as cellular precipitation. But before I do that, let me again reiterate some of the important aspects of spinodal decomposition. You remember I started with such a kind of a phase diagram with a miscibility gap marked by a dome like picture. So, as you know, if I take an alloy with the composition x0, at temperature T1 it will have a single phase alpha. Now, once I quench this alloy to T2, if this alloy has any small composition fluctuations, those fluctuations will grow without any nucleation, and microstructure will be typically looking like a two-phase microstructure decomposed from a single phase. And we have shown that this kind of phase diagram is a resultant of the free energy versus composition diagram shown at the bottom. Remember, these pictures are directly taken from the book of Porter and Sterling, and you see here there is a hump in the free energy curve. Not only that, I told you that the inside dotted curve, which is marked as a chemical spinodal hair, is basically defined by these 2 points where the double derivative of free energy with respect to composition is 0. That means curvature is 0. It is very clear that there is a concave and there is a convex curve, and they meet at these points, therefore curvature is 0. This is something which we start with it. Now, any alloy composition which is which is lying in the region between this dotted curve and the solid one, that is from this point to this point or from this point to this point, transformation will happen by nucleation and growth. Basically, that is the mode normally almost all the phase transformations undergo. So, now question is this, and how the things happen. I told you this picture I have drawn in the last class, that if you have a composition fluctuation, then fluctuations grow, and then you have a phase separator regions with the composition x2 and x1, which is A reach and other one is B reach, as seen in the phase diagram in the last picture also. And this requires an uphill diffusion, that means diffusion of the atoms against the concentration gradient. That is why you call it uphill diffusion, but as I showed in the first lecture, that this diffusion is down the chemical potential gradient. So, therefore, the diffusion happens down the chemical potential gradient, but the way it takes place, it looks like it happens up the concentration gradient. A goes to the A reach region, B goes to the B reach region. So, that is why it is called a compositional partitioning. And I discussed to you the free energy expressions, as you said that this you see here very clearly there is a wavelength of fluctuation. That means the composition fluctuations can be fitted with a particular sinusoidal or cosinusoidal or any other type of fluctuations, and that means there is a wavelength of fluctuations, and that is very important. And wavelength of fluctuations basically is related to the characteristics time constant of the transformation, which is given by minus lambda square by 4 pi square d, and I told you in the last lecture also that the interdiffusion coefficient d within the chemical spinodal is negative. That is what is the meaning of the uphill diffusion basically. Now, in order to know the wavelength, I discussed in the last class about this. In order to know the wavelength of the compositional fluctuations, we need to develop free energy expressions. That there are 3 free energy components. One is the chemical free energy part, which is given by half double derivative of g with respect to x multiplied by delta x square, where the delta x is the composition fluctuations. This is very simple because there is no need of discussing on this much more. Basically, once we have homogeneous phase, decomposing it into two phases, one with the x plus delta x, other one is x minus delta x compositions, or x0 plus delta x and x0 minus delta x, that is what is written in the book. Then it is very easy to show that the chemical energy change will be by this amount, half of double derivative of g respect to x into delta x square. And as you know, there is always interfacial energy because of this compositional fluctuation. That is what I discussed in the last class, that is what is called gradient energy, and gradient energy is given by this expression. Okay, gradient energy is given by, what is that? Yes, gradient energy is given by this expression, delta g is equal to k delta x by lambda square, where delta x is the amplitude of the fluctuations and lambda is the wavelength, and that means delta x by lambda is basically nothing but a compositional gradient, is it not? Because one is the composition, other is the length. So that tells you a compositional gradient, and the square of that multiplied by factor gives you the delta g gamma, that is the interfacial energy or gradient energy term. And lastly, most important thing is that because of the compositional fluctuation, there may be difference of the lattice parameters of the phases, and these can lead to what is known as strain energy or coherency strain energy. Sometimes people define that, and this obviously led to the misfit of the lattice parameters, that we know, that I defined in the last lecture also, and therefore Gs or delta Gs is given by the elastic constant or Young modulus multiplied by the delta square, or delta is, small delta is nothing but the your misfit. Now we can actually get an equation, and finally we showed you that in the limits of temperature and compositions, the lambda, when the lambda become infinity, this condition to be satisfied, and for anything, for whatever lambda, possible lambda is basically this condition to be satisfied. You see, these are boils down from this master equation of g, delta g. So thus minimum possible wavelength decreases in increasing the undercooling below the coherent spinodal. Now this equation which I showed you here, delta g square by dx square equal to minus 2 eta square E prime multiplied by Vm. These parameters I have defined in the last class also, where Vm is the molar volume, E prime is basically E divided by 1 minus nu, where nu is the Poisson ratio and E is the elastic modulus or Young modulus, and eta is nothing but 1 by A dA by dx. Okay, so therefore, if this line which is defined by this equation is known as a coherent spinodal, because it only talks about coherence strain with the available chemical potential, a chemical energy, that is because lambda is infinity. So therefore there is no gradient energy term. So now I want to just discuss with you that these are the things which I discussed in detail. Now we can actually do the analysis properly. As you see here, this is the chemical spinodal. Okay, or this is the chemical spinodal you see here, and within the chemical spinodal you have a coherent spinodal. Okay, and these actually solid lines which I tell you incoherent miscibility gap and coherent miscibility gap. Okay, so spinodal decomposition is leads to all kinds of change or the lines in the phase diagrams, but you do not need to remember everything. This you need to only remember the miscibility gap, that is defined by the dome, and then you have within the dome you have something known as a chemical spinodal, and that chemical spinodal is given by the condition that double derivative g with respect to x equal to 0. That means the curvature of the free energy curves is 0, and those, for if I do that kind of analysis, which I shown you here, if I do this kind of analysis for every temperature, this is done as temperature T2. If you do any temperature, you will get these 2 points, okay, which is defined by this equation double derivative g with respect to x equal to 0, and then you can actually generate this chemical spinodal. This is what is chemical spinodal. Now similarly, if I use this equation, this one, double derivative of g with respect to x at any temperature equal to this one, that is lattice parameter change, which can give you the coherence strain, then we can actually get another set of points which provides us the coherent spinodal. So there are 3 important aspects which you must remember. One is this dome solid line, okay, and that solid line tells you incoherent spinodal. Okay, then within that solid line you have a chemical spinodal given by the double derivative of g with respect to x going to 0 for every temperature. from the free energy curves, and within this chemical spinodal what you are going to have is a coherent spinodal. So, remember within the chemical spinodal the phase transformation is given by growth, no nucleation is required because it is a spontaneous process. Any fluctuations present in the material, composition fluctuations will grow without any barrier, but the compositions which are between incoherent and the chemical spinodal, we will have nucleation and growth. Transformation is same as like a precipitation. Okay. From alpha, alpha 2 or alpha 1 will precipitate. So, there is no difference of the precipitation and these transformation with any composition which is lying between the incoherent spinodal and the chemical spinodal. And within the chemical spinodal, we have something known as a coherent spinodal. That means the spinodal which is dictated by the coherence strain. The free energy available, chemical free energy available for the system is completely spent in basically this in taking care of the coherence strain because of the lattice parameter difference or the misfit between the two phases. These are actually very general I am speaking, but because this is undergraduate or for the mostly undergraduate students and some preliminary postgraduate students, if you want to know in detail about this kind of things, you need to go through the literature very nicely. And in this regard, I like to bring the work done by J.W. Khan long back 1950s, 60s, and to understand it. There are some papers available in literature which is there in the book also, you can read it, but fundamentally this is a very important phase transformation, that is what you should remember. Okay, some of the microstructures which you have seen there, this is one you can see here. There is a coercion spinodal microstructure for aluminum, zinc, magnesium alloy, which is hallucinated treated at 400 degrees Celsius for 2 hours and then etched at 100 degree for 20 hours. And this is basically TM microstructure. You show the composition fluctuations very easily, although it is coercion because it has the spinodal decomposed zones has coercion a little bit. Okay, so I will not talk about much of that other than saying that you need to study spinodal decomposition a little seriously, because this is something which you have not been subjected to or you have not been taught in your previous curriculum. Okay, that wraps up the spinodal decomposition part. Now I just start the whatever time I have, I will start these new transformation which is known as cellular precipitation. I discussed a lot about precipitations. Remember that precipitation is one of the major route of transformations. Aluminum copper silicon, aluminum magnesium, many alloys undergoes, nickel aluminum undergoes precipitation type of phase transformation, and these are very important because this is one of the unique way of imparting strength to the material. And I discussed extensively on this part for aluminum copper, aluminum silver systems, I remember. So, but things are similar. So, now for the next few lectures what I am going to take at the last part of this course, I am going to concentrate on some special phase transformations. Okay. There are many special phase transformations, but it is not possible for me to discuss all of them. I will take few ones. Okay. First I will take the thing of cellular precipitation. It is there in the book of Prof. Sterling as well as of the Jina and Chaturvedi, you can read it in detailed manner. So, gain boundary precipitation, cellular precipitation is related to gain boundary precipitation, in fact it is related to gain boundary migration also. So, gain boundary precipitation does not always need to happen or need to always result in gain boundary phases or Woodman certain patterns. As probably you have, if you go back to my lectures on the phase transformation sequence of the hypo or hypereutectoid steels, then you have seen that for the hypoeutectoid steel, the alpha phase, which is proeutectoid phase or primary alpha, proeutectoid alpha rather, it is better way to define, forms along the gain boundaries of the existing austenite, because the composition of the steel is less than 0.76 weight percent of carbon. So, therefore, the transformation will begin with the formation of alpha from the gamma austenite. Similarly, if you go on the hypereutectoid sides, the transformation will begin with the precipitation of the cementite. And if you see the look at the microstructures which I have shown you previously, the cementite basically forms as a discontinuous precipitates on the gain boundaries of the existing gamma. And because cementite is a carbon rich phase, that is how the carbon of the austenite is reduced before it reaches the eutectoid transformation temperature. And therefore, the remaining austenite whatever will be remained with the chemical compositions of 0.7768% carbon will be transformed to perlite at a temperature less than about 727 degrees Celsius temperature. Okay. So, but this this is one way of precipitating phases along the gain boundaries, but it does not mean that this will always happen. Okay. And I also showed you that some of these alpha, pro-eutectoid alpha can form Widmanstätten like a plate like things. It is just like you have a gain boundary. If you have a gain boundary, then it forms along the gain boundary as a, if this is the gain boundary, it forms like along the gain boundary, then this kind of plates happen and form. So, this is alpha, pro-eutectoid alpha, okay, and this is basically called Widmanstätten alpha, because this looks like forms like a plate, okay. This is alpha plates, and this is the gamma boundary. Okay, that is the one way, or it can actually happen like a precipitate along the boundary between that. Cementite also forms that way. But gain boundary precipitation does not always lead to gain boundary allotropy or the Widmanstätten. Okay. There are different modes of transformations, and cellular precipitation is one of those. Essential feature of this transformation is this picture, as you see here, figure 5.50 in the book of Porter and Sterling, is that this transformation is that boundary on which this precipitation happens, it moves along with the precipitation. In case of those two transformations I told you, Widmanstätten and the cell and the precipitates of the primary or pro-eutectoid alpha or cementite, basically the gain boundary does not move, but here gain boundary moves. That is what is shown in this picture. So, the transformation is that boundary moves along with the going tips of these precipitates, and this leads to cell like feature. You see, this is cell, correct? In the solidification, cells form cells, and then cells breaks down to it and right. That is why it is called cellular transformations. The transformation equation is exactly same, alpha going to alpha prime plus beta, okay, that is same, where alpha prime going to, not alpha. So, alpha prime is a supersaturated solid solution and alpha is basically the equilibrium or rather phase with the lower thermodynamic excess of solute, and beta is basically equilibrium precipitates. That means, if you have a supersaturated alpha prime, it's the beta precipitates out of the alpha and leading to alpha having less solid presentations. Okay. So, now question is that this kind of mechanism by which this transformation happen is still debated, it is not yet understood. As I told you, just I will in another couple of maybe 10-15 minutes, 10 minutes time, whatever time I have in this lecture, I am going to show you few microstructure and probably try to explain you how things happens. The gain boundary mechanism by which the gain boundary nucleation develops into cellular precipitates, it differs from one alloy to other alloy. That is the one of the problem. That is why it is not fully understood. Let us look at magnesium aluminum system, which is widely studied. Magnesium aluminum phase diagram, part of the phase diagram on the magnesium end is shown here. You see here, there is a liquid, then alpha and the beta. Okay. Now, if I take an alloy compositions about close to 0.1% of aluminum or 0.1 mole fraction of aluminum and start cooling it down, then beta will precipitates. It is very clear, because at high temperature it is a single phase alpha supersaturated solid solutions. Now, if you cool it down, beta must precipitate. This is just like aluminum copper phase diagram, looks like similarly. So, but what actually happens? This picture is basically shows you the precipitates of the magnesium 17 aluminum 12. This is this beta. Beta has a very complex composition. It is not a complex, it is basically intermetallic, that is why, and it alloy composition is a magnesium 9 atom percent aluminum. It was solutionized I think at 410 degrees Celsius temperature to make it completely alpha, followed by quenching I think it was quenched, given 2 stages, basically solutionized and then quenched to 220 degrees somewhere there, okay, here 220 degrees, and then aged for about say I think 20 minutes at 200, okay. And then followed by, so the aging done was at 277 degree, sorry what I am saying, yeah, it was first solution treated at 410, then quenched to a temperature 220 for 20 minutes, followed by 90 seconds at 277 degrees Celsius, finally water quenched. So 220, then again heated up to 277, that is close to 300 somewhat there, okay, then it was quenched. So now the picture looks like eutectoid eutectic solidification, okay, you see here, but what you see here, this was the prior gain boundary between the 2 phases, between the 2 grains of alpha, that is alpha, okay. But then beta precipitates along the gain boundary, but as you see here the beta precipitates, the gain boundary moves and it develops cells, right, you can clearly see that it develops cells. I can draw and show you that few of them, and then obviously cells have grown, you can see here this is the precipitates, these are the precipitates which are formed, and it looks like a eutectoid transformations, but it is not the microstructure looks like. Okay, so then what actually happens? The growth of the precipitates, as you know, requires wear. This is a diffusional transformation, that means you are forming a phase beta which is a distinct different composition as compared to alpha. So to form that, to precipitate it out, you need diffusion of the solids, most importantly diffusion of aluminum, that is required. So now question is this, the growth of the cellular precipitates required partitioning basically, or partitioning your solute at the tips of the precipitates, okay, because this is growing into the gain boundary. So this requires this solid partitioning at the tips of the boundaries. Now question is this, that means that boundary has a role, right, very importantly, obviously gain boundaries are the important regions of the phase transformation, whether it is a nucleation or it is a growth, gain boundaries play a very important role. So now the question is this can occur in 2 ways, obviously if you think it, one by lattice diffusion, okay. How? Yeah, through the lattice, through the bulk of the phase it can happen, the diffusion or the partitioning of the solids which is basically done by diffusion, this can happen, or it can happen along the gain boundaries, things can actually diffuse on the gain boundaries. But you know the studies which are done very nicely, which I will discuss in the next class in detail later on, showed that it is not the lattice diffusion, rather it is the diffusion along the gain boundaries which plays role, which is have more governing features about that. So partitioning by lattice diffusion requires solid concentration gradients out of the cell boundary, obviously. When something is growing by lattice diffusion, it requires a compositional gradient ahead of the gain boundary, otherwise this partitioning will not happen. But on the other hand, if it is happening, diffusion happening through the gain boundaries, so because precipitates is sitting, the tip of the precipitate is sitting at the gain boundaries, so this gain boundary can act as a channel for the transport of the solids to reach at the tip of the precipitates, and the precipitates can go further. And this is the reason why the gain boundary moves along the precipitates, because gain boundary is feeding, gain boundary is acting as a feeding channel for the solids partitioning, and that is why the gain boundary has to move, because if the gain boundary is stagnant, the precipitate will move ahead. That is what happened in Widmer-Stratton plates. Precipitates nucleates at the gain boundary, then they grow like a plate. So when they grow like a plate, diffusion is happening because in the grain, within the grain, and this diffusion happened because of the compositional gradient which is developed ahead of the precipitate or ahead of the Widmer-Stratton plates, right. But here the precipitate is always present or the tip of the precipitate is present along on the gain boundary. Okay, it is like this. Okay, let me go back to this picture. Precipitate is always present, tip of the precipitate is always present at the gain boundary, tip of the gain boundary. So what I mean, gain boundary, which is which is the better, faster path of diffusion for the solids, can actually can act as a feeding channel for the solids to reach at the tip of the precipitates, and the precipitates then grow. As the precipitates grow, it takes along the gain boundary, along with it, and that is why the gain boundary actually move from B to C to D, because the gain boundary is slowly moving into that, and gain boundary moves to one of the grains, and this is very fascinating kind of phase transformations. Okay, I will not discuss the way things happens. Let me just show you one picture before I stop today. That here, this is basically a shell form. This is basically again aluminum magnesium alloy. This is during aging treatment at 2 temperatures, one at 220 degrees Celsius temperature for 30 minutes, and it was followed by 277 at degrees Celsius for again 30 minutes, and then obviously it is water quench. And you see, this is the alpha grain, okay, and this is the beta precipitates, the black color ones you can see here, black color things which are beta precipitates, and this was the gain boundary, and they form like a cell, right. You can see here, this is better here, see. This is the gain boundary, the Moir fringes are observed in the gain boundary, because this is a transverse electron micrograph. So now as these precipitates grow, they are taking the gain boundary along with it, and that is only possible when the solids actually diffuses through the gain boundary acts as channel for the solid diffusions. Well, the detailed proof of this, how this precipitation is governed by gain boundaries, has been done. I will discuss you in the next lecture, and then I will start on the transformation happenings in the next lecture itself.